Alrighty then, seems that I'm live. So today I I started actually something the last time I was streaming. Okay, I don't need you for now. So I started my journey into understanding the fast inverse square root algorithm. The first time I came across this algorithm was in an article by, I don't remember exactly who wrote it, but the article itself spoke about this amazing way of handling shadows inside ID Software's Quake game. I don't know which Quake it was exactly, maybe Quake 3 or something. So I remember the first time I came across this. It even has the comments, I remember. It was like stumbling across old Egyptian hieroglyphs. I couldn't understand anything. And as time went by, I would randomly see and notice these. I would randomly see and notice these moments in which the algorithm would reappear again, like in other articles or in discussions with friends and colleagues. So what I decided to do now is actually the following. I wanted, so this is quite a big article. I want to read it. I want to understand it, and I want to uh, grasp this after, finishing the university, after being here, working in the industry for 7 8 years. I want to know whether I understand this. So let's start. Everything I know about the fast inverse square root algorithm. Yeah, by the way, this was written by Francis R. Stokes. All right. So the fast inverse square root algorithm, made famous though not invented by programming legend John Carmack in the Quake 3 source code, computes an inverse square root 1 over square root of x with a bewildering handful of lines that interpret and manipulate the raw bits of float. It's wild. All right. All right. All right. All right. All right. So the first thing that I will need some help with my friend ChatGPT is okay, I can remove this. Maybe I can even put this here. Yeah. So programming legend John Carmack in the Quake 3 source code computes an inverse square root with a, so this is an inverse square root. So my first question will actually be, why is the square root algorithm useful? Okay. By the way, I'm also gonna use my tablet. And here's how it looks. I also have a new wallpaper for it, but let's not jump ahead of ourselves. So the square root algorithm is useful because it enables the efficient computation of square roots, a fundamental mathematical operation with applications across numerous fields. Here are the reasons why square roots are important: mathematical and computational foundation, engineering and physics, computer graphics, financial modeling. Okay. What about using it in video games? Why am I every time I move to the top left, it, for some reason, No, it doesn't work. I need to do it fast. Okay, I don't use this. So the square root algorithm is especially important in video games because many calculations involving physics, graphics, and gameplay mechanics require the square root operation. Here are specific ways it is used in the video games. Player and object positions. Okay, so this is a formula that determines the distance between 2 points in 2D or 3D space. I already worked on this. Let me just show you. Here. So basically this is the most simplest vector arithmetics. What happens here is that I have this dot and I just wanted to calculate the distance from the center to this dot. Oops, let me just move this. So I just used the Pythagoras theorem, but I assume, let me just move this for now. I assume it will get more complex. So let's go back here. So it's wild. So this is the method. It's called float q underscore r square root. So I'm taking a number. So what is he doing here? Can increase this a bit. Yeah. So it takes a long variable. It creates a float variable. It creates a 3 halves. Is this written like half? Wait. Is this written like halves? Halves instead of this? Is it halves or halves? Half can serve as a noun, pronoun, adjective, or adverb. To halve is a verb, meaning the plural of halve is halves. Can we say 3 halves? All right. Let me read through this. So it's a const float. It's called 3 halves. Then we are starting to do something. We are starting to multiply the number that we provided with 0.5. Then we set the number to y. So wait. I'm dividing this, right? Let me open this. So if my number is 5, so if I'm dividing it with 1/2, so it's gonna be 5. Okay, so I'm basically dividing it in half by multiplying it with 0.5. Then the number is set to epsilon or y. The number is set to y. Then I have a pointer. Okay, here I'm already. Now these three are worrying me. So in this article we'll get into what's actually happening at the mathematical level in quite a bit of detail, and by the end, with a little persistence, you'll come away actually understanding how it works. Great, that's what I wanted. The first time I came across this algorithm, the only thing I wanted to do is to learn how it works. I'm not the first to write about this algorithm, and I surely won't be the last, but my aim is to show every step of the process. Okay. All right. A lot of really fantastic resources out there. Still skip. All right. So it's important to know that this algorithm is very much of its time. Back when Quake 3 was released in 1999, computing an inverse square root was a slow, expensive process. The game had to compute hundreds or thousands of them per second in order to solve lighting equations and other 3D vector calculations that rely on normalization. These days, on modern hardware, not only would a calculation like this not take place on the CPU, even if it did, it would be fast due to much more advanced dedicated floating point hardware. So this is a slow process. Alright, so this is the algorithm again. So this is the code, more or less exactly as it appears in the Quake 3 source, including the comments. Personally, I think evil floating point bit level hacking, what the fuck, is a fantastic explanation, but I do want to dig in quite a bit further. Okay. So why this works is because the raw bit pattern of a float, when interpreted as a 32-bit signed integer, essentially approximates a scale and shift log function. All right. I have a couple of questions regarding this paragraph on. I always miss regarding this paragraph on the inverse square root. What does the author mean by raw bit pattern of a float when interpreted as a 32-bit signed integer? What does it mean? What does it mean when it essentially approximates a scaled and shifted log2x function? Let's break down, great questions. Let's break down the concepts from the paragraph step by step. Raw bit pattern of a float when interpreted as a 32-bit signed integer. So what is a raw bit pattern? A floating point number in a computer is stored as a specific binary representation following some standard. These okay. So I just remember this. I learned about this at the uni. Basically, in order to properly represent floating point numbers, consider that they have a decimal point and they have numbers before and after the decimal point. We need to do some hoop jumping, basically. We have 1 bit for the sign, so whether the number is positive or negative. Then we have 8 bits for the exponent, which is used for scaling the number, and 23 bits for the mantissa, which is used for precision. So a floating point number is decoded using the IEEE 754 rules to extract its value. However, in this context, the algorithm ignores the rules and treats the same 32 bits as if they represented a standard 32-bit signed integer. One of the key ideas but how raw bit pattern of okay, so it's talking about the bit representation of it, because I was asking myself, how could it represent, how could a random sequence of numbers, decimal numbers, represent a log2 function? Okay, let me just do this. Can you give me an here's an example. So a floating point number like 3.14 might have a binary representation 32 bits as following. .14. How to understand the binary representation of a floating point number? Yeah, this is what I want. So this is the standard. Then we have the sign. The sign is 1 bit. 0 stands for positive and 1 stands for negative. In our example, 3.14 is positive, so the sign bit is 0. Then we have the exponent. So wait. Encodes the power of 2 that scales the number stored with a bias of 127. I don't understand this. Hey, thank you so much. Thank you. Thanks a lot. I'm trying to understand this inverse square root algorithm. And for that I have to go back to the basics. And the basics are how are numbers represented in our computers. Okay. Thank you so much, Sadat. Hope you have a great day. And encodes the power of 2 that scales the number with a bias of 127. So 314 is in this range. But what does it mean that it's stored with a bias of 127? For 340 we need to determine the actual exponent first. So this is in this range. So the exponent is 1. The biased exponent is 1 plus 127, which is 128, which is this in binary. And now mantissa. Normalizing 314. Floating point numbers are normalized to the form 1 point fraction times 2x. Man, I think ChatGPT is just overcomplicating shit. I mean, what is this meaning? Okay. Essentially approximates a scaled and shifted log2 function. Understanding log2, so it's not log2, it's log with a base of 2. Okay, let me subscribe to your channel as well, sorry. Just a second. Just a second. Here you have a new subscriber. I guessed you were Turkish by your surname. Essentially approximates a scaled and shifted log 2 log 2 with a base of 2. Okay, let's go back here. So logarithms have a bunch of rules, properties, and identities that can be exploited to make computing the inverse square root easy for a computer using only simple operations like adds or shifts. So logarithms have a bunch of rules. Fuck me. I mean, this would be great if I remember anything from logarithms in high school and university. I mean, I remember a lot, but ah, nice. So he will also explain the representation. Amazing. So I don't need ChatGPT at all. But let me. Okay. So these are the 32-bit floats and their representation here. All right. So what do we have here? We have here the following thing. I'm just gonna use another color. So it's a structure which I'm gonna call row float. So what do I have? I have a mantissa, 23 elements. I have the exponent, which is 8. And the sign, which is 1. Okay. So I'm just gonna remove this, hide this. So what is what? So the sign, okay, the sign is simple. The sign 1 bit, which indicates whether or not the number is positive or negative. Exponent 8 bits, which are used to dictate the range that this number will fall into. And mantissa are 23 bits, which literally specifies where exactly in the range this number lives. Okay. So we have an equation that shows how the actual numerical value good night, Sarat. What time is it there? For me, it's 11:12 in the night. Yeah. Good luck to you too. Okay, 1 bit which indicates whether or not the number is positive or negative. And but how is the exponent dictating the range that falls with this number? Like, this is not concrete at all. This is not math. Which literally, what does it mean? So this is the number. This is the sign. Okay, the sign is really simple. Basically, based on 0. Wait, the sign is a 1 bit, so it can be only 0 or 1. then I do this and I do this. So this is the mantissa. No, this is the mantissa. Whatever M is, I have no fucking clue. What is B? B is 127. Where the fuck is B here? Ouch. I hit my elbow on this. How is this? Ah! N. What the fuck is N? So N is the number. Where is B here? Ah, E is E minus B. Ah, this is B. So it's a constant. So if it's 0, it's going to be minus 1. If it's 1, it's going to be a positive 1. And 1 multiplied by 1. 1 multiplied by 1 is 1. And negative 1 multiplied by negative 1 is 1. Times E. Now this is what I'm interested in. How did this appear all of a sudden? Okay. Notice that instead of simply multiplying by m, we multiply by 1 plus m. This ensures that when m is 0, we get 2e, and when m is 1, we get 2e plus 1. The full range. Let's take an example like the number minus 1 to minus 1.724. Okay, so this is 1. Wait. No, but this shouldn't be so minus 1. Wait, so this is not correct. They can't both be minus 1. I'm a smooth skin. So this is the number, minus 1.724. All right, maybe before I jump into okay, let's do this first. How are 32 bit floats represented on a computer? Explained. No, this doesn't seem like it would be helpful. floating point representation. Yeah, so this is the same standard that this GitHub article is talking as well. So the representation issues for floating point numbers are more complex. There's a series of floating point representations. Okay. For various ranges of the value. So this is the standard. Okay. So this is how it looks, the standard. So I have the sign, I have the exponent, I have the fraction. Sign is positive or negative, and we can write this like this. But this is not good. How are floating point numbers stored IEEE 752? Is there a better article, or maybe YouTube? Floating point numbers okay, this is the one.
There are two main ways to represent real numbers in binary: fixed point and floating point. I've talked about these in detail in other videos, but to quickly remind you, fixed point representation fixes the position of the binary point within a register, and therefore fixes the sizes of the whole number and the fractional parts of any real number stored in that register. Place values to the left of the point are bigger than 1, and place values to the right are smaller than 1. Each place value is double that of the place value on its right. Exactly where the point is fixed depends on the way that particular computer system has been designed. Fixed point binary can greatly simplify the processing of real numbers, but it imposes big limitations on the range and precision of the real numbers that can be stored. Floating point representation is the most common way of encoding real numbers in binary. It uses a binary version of the standard scientific notation with a base number, the so-called mantissa, and an exponent. The floating point format covered in my other videos assumes there's an imaginary binary point located immediately to the right of the leftmost bit in the mantissa, the so-called sign bit. The value of the exponent specifies how far to the left or to the right the binary point should float in order to obtain the actual value in the register. The number of bits available for the exponent governs the range of the number that can be represented, that is, how big or how small, and the number of bits available for the mantissa governs the precision, that is, the accuracy of the number. This floating point format employs two
Am I cooked with
complement to represent negative values in binary. It uses a binary version of the standard scientific notation with a base number, the so-called mantissa, and an exponent. The floating point format covered in my other videos assumes there's an imaginary binary point located immediately to the right of the leftmost bit in the mantissa, the so-called sign bit. The value of the exponent specifies how far to the left or to the right the binary point should float in order to obtain the actual value in the register.
So the value of the exponent,
the number of bits available for the exponent governs the range of the number that can be represented, that is, how big or how small, and the number of bits available for the mantissa governs the precision, that is, the accuracy of the number.
okay.
This floating point format employs 2's complement to represent negative values in both the mantissa and the exponent.
Wait. Is this... Okay. Sorry, my bad. Let me continue this.
Exponent. Historically, floating
Okay.
point formats have varied from computer to computer. For example, the number of bits assigned to the mantissa and the exponent could vary.
Oh no. Wait.
Of the real number. Exponent specifies how far to the left or to the right the binary. Historically, floating point formats have varied from computer to computer. For example, the number of bits assigned to the mantissa and the exponent could vary. For a fixed-sized register, more mantissa bits means better precision, but this comes at the expense of exponent bits. So better precision means a smaller range. Some formats would place the mantissa bits to the right of the exponent bits, and some would place them on the left, as shown here. Some formats would use sign and magnitude to represent negative values, while others would use 2's complement. It wasn't until 1985 that the Institute of Electrical and Electronics Engineers defined a standard format for floating point binary, a format that is used in most of today's computers. So, in this video, I'll describe the IEEE 754 standard for representing floating point binary numbers.
All right.
The IEEE 754 standard defines the layout of a 32-bit.
Okay, so we have a sign bit, we have an exponent, and we have a mantissa. Amazing.
Single precision floating point number, as shown here. If you're a programmer, you may be familiar with the variable data types single and double. Online help about these data types includes the range of values that can be stored. I'm going to focus on single precision for now. Notice that the sign bit is the leftmost bit, followed by an 8-bit exponent, and then a 23-bit mantissa. The mantissa actually has 24-bit precision, but only 23 bits need to be stored. More about that in a moment.
Okay.
Double precision also has a single sign bit on the left, followed by an 11-bit exponent, and then a 52-bit mantissa, giving a total of 64 bits instead of 32. Let's look at an example. I'm going to convert the denary value, 19.59375, into IEEE 754 standard, single precision, 32-bit floating point binary. The first step is trivial. Determine the sign
Please do. So 0 is positive, 1 is negative.
bit. If the number is positive, the sign bit will be 0. If it's negative, the sign bit will be 1. This is a positive number, so the sign bit is 0. In the second step, convert the denary value into pure binary. In other words, convert it into a fixed point format. At this stage, you can treat negative numbers as if they were positive, because you've already established the sign bit. For an uncomplicated...
Wait. Sorry, I was setting up my...
In the second step, convert the denary value into pure binary. In other words,
Convert the number into pure binary.
convert it into a fixed point format. At this stage, you can treat negative numbers as if they were positive, because you've already established the sign bit. For an uncomplicated number like 19.5 or 19.25, you can easily determine the place values you need to make up the number. But 19.59375 is not obvious. A common approach involves repeatedly halving the whole number part and repeatedly doubling the fractional part. 19 divided by 2 is 9 with a remainder
What? 19 divided by 2 is 9, and we have a remainder of 1.
1. 9 divided by 2 is 4 with a remainder of 1. 4 divided by 2 is 2, remainder 0. And 2 divided by 2 is 1 with a remainder of 0. And there's 1 remaining at the end. If you think about it, there's always going to be 1 at the end. The remainders give you the bit pattern for denary 19.
Alright, this makes sense.
To convert the fractional part, you repeatedly multiply it by 2. 0.59375 times 2 is 1.1875.
Okay.
The 1 in front of the decimal point of this result is the first binary digit you need. The fractional part of this result is then multiplied by 2. 0.1875 times 2 is 0.375. The result starts with 0, which is your next bit. 0.375 times 2 is 0.75. Another 0 is generated. 0.75 times 2 is 1.5, so this time you have a 1. And finally, 0.5 times 2 is 1. This is when
Wow, this is interesting, but also...
to stop, when the fractional part is 0. This method of converting from denary to binary is particularly good for spotting a recurring sequence of bits, as you'll see later. Now, you need to normalize the pure binary representation.
So normalize to determine the mantissa and the unbiased exponent.
Binary point is moved so that only one non-zero bit remains to the left of it. In this case, the point is repositioned 4 places to the left. To get
Wait.
bits, as you'll see later.
Okay, so this is 1, 0, 0, 1, 1. This is our binary representation of the number 19.
Now, you need to normalize the pure binary representation. The binary point is moved so that only one non-zero bit remains to the left of it.
Wait.
In this case, the point is repositioned 4 places to the left.
point is repositioned 4 places to the left.
To get the point back to where it was, you would have to float it 4 places to the right. So now you have the value of the exponent, namely 4. The normalized binary value is therefore 1.00111111 times 2 to the power of 4. In step 4, you need to calculate the biased exponent.
Oh, you must be fucking kidding me, man. This
You're
is...
simply following 1.0.
Is this something complex for me? What the fuck?
011 times 2. You need to normalize the pure binary representation. The binary point is moved so that only one non-zero bit remains to the left of it. In this case, the point is repositioned 4 places to the left. To get the point back to where it was, you would have to float it 4 places to the right. So now you have the value of the exponent, namely 4. The normalized binary value is therefore 1.00111111 times 2 to the power of 4. In step 4, you need to calculate the biased exponent. If you're simply following a recipe, all you'll need to do is add 127 to the value. In this case, you'll get 131, and then convert that into an 8-bit unsigned binary integer. I'll explain the principle and reasoning behind the biased exponent in just a moment, but for now, let's finish off this conversion.
Okay.
The final step is to remove the leading 1 from the mantissa. The leftmost bit of the mantissa is always going to be 1 for any real number that we want to represent in this format, so there's no need to store it. We know it belongs there and that it needs to be put back before doing it.
Okay, I understand the reasoning. He moved the dot, the point, he moved it left, and this will be the exponent that we are multiplying with. So this exponent is 4, we add it to 127, then we convert the result that we get to a binary representation, and this is our exponent. But my question is, why are we doing this? Why is this happening?
In actuality then, this format has a 24-bit mantissa, but we only need to store 23 bits of it. All that remains to be done now is to pad out the mantissa with trailing zeros. Now, let's say a little bit more about the way the exponent is encoded.
Okay.
We need to add 127.
Bro.
What's the benefit of this approach? Suppose for a moment that you have a 4-bit exponent. It's easier to see how this works with only 4 bits. Exactly the same principle applies to an 8-bit exponent, or indeed an exponent with any number of bits. With 4 bits, you can see that we have 2 to the power of 4. That's 16 different combinations of 1s and 0s. So a 4-bit exponent can have one of 16 possible values. If you only ever needed to represent positive exponents, then you could represent all of the values from 0 to 15.
Okay.
These bit patterns are easily converted into unsigned integers with a simple place value gadget. But since you also need to represent negative values, you have to sacrifice some of the positive values. One way to do this is to use 2's complement, and you can use a modified gadget to do the conversions.
So 1011 is 1011. So it's either sorry, it's either 1011. It's either 11 in decimal in only positive representation, or -5.
The most significant bit has a negative place value. 2's complement allows for an equal number of positive and negative values.
421 011 011.
Assuming that 0 is a positive value. Notice how all of the negative values begin with 1 and all of the positive values begin with 0. This is why the leftmost bit is called the sign bit in 2's complement. Now, suppose you wanted more positive values than negative values. This requires a different approach. Here you can see there are only 5 negative values.
Wait.
0 positive value, 2 negative values. You have to sacrifice some of the positive values. One way to do this is to use 2's complement, and you can use a modified gadget to do the conversions. The most
So this is called 2's complement.
bit has a negative place value. 2's complement allows for an equal number of positive and negative values, assuming that 0 is a positive value. Notice how all of the negative values begin with 1 and all of the positive values begin with 0. This is why the leftmost bit is called the sign bit in 2's complement. Now,
What?
Now, suppose you wanted more positive values than negative values. This requires a different approach. Here, you can see there are only 5 negative values, but 10 positive values. Notice that the denary value, -5, is represented with 4 zeros, and that the denary value 0 is represented with the bit combination 0101. Because of this peculiarity, if all these represent positive exponents, then you could represent all of the values from 0 to 15. These bit patterns are easily converted into unsigned integers with a simple place value gadget. But since you also need to represent negative values, you have to sacrifice some of the positive values. One way to do this is to use 2's complement, and you can use a modified gadget to do the conversions. The most significant bit has a negative place value.
So the most significant bit has a negative place value, which is the 1, the leading one, and basically all the ones are representing negative values.
2's complement allows for an equal number of positive.
But how then do I get these? How do I get -5 here?
Negative values, assuming that 0 is a positive value. Notice how all of the negative values begin with 1, and all of the positive values begin with 0. This is why the leftmost bit is called the sign bit in 2's complement.
So the leftmost bit is called, okay, the sign bit.
Suppose you want more positive values than negative values. This requires a different approach. Here, you can see there are only 5 negative values, but 10 positive values. Notice that the denary value, -5, is represented with 4 zeros, and that the denary value 0 is represented with the bit combination 0101. Because of this peculiarity, you can no longer convert directly between binary and denary. You need to perform an additional step. Suppose you wanted to find the bit pattern that represents, say, denary 3. You need to add 5 to 3 first, because there are 5 negative values. And then you can convert the result into an unsigned binary integer. 5 plus 3 is 8, and 8 in unsigned binary is 1000.
Okay, so in the middle example, he used 2's complement, but now he put negative values at front of this, and we spared some positive values. So basically, if we want to do the tree, we need to know how many negative values we have. We have 5, so I add 5 to 3, and I get 8, and I get the binary value of 8, and that's the binary value 1000 of 3 using this third column.
To find the bit pattern for, say, -3, you should employ exactly the same method. Add 5 to -3, which is 2, and 2 in unsigned binary is 0010. If you want more negative values than positive values, you can allocate the bit patterns differently. In this case, there are 9 negative values and 6 positive. To find the bit pattern for, say, denary 4, you need to add 9 first. 9 plus 4 is 13, and the unsigned bit pattern for 13 is 1101. The same system is being used here, but this time there are an equal number of positive and negative values. To get the bit pattern for any one of these values, you first need to add 8 to the number that you want to encode, because that's how many negative values there are. This final set favours positive numbers. This is actually how the IEEE 754 standard works. With 4 bits available, there are 2 to the power of 4
Wait.
minus 1, that's 8. Minus 1, that's 7 negative values. So 7 is the number that you need to add to any value that you want to encode before converting it into unsigned binary.
Okay, it's so the 2 is raised by 4 because we have 4 digits in the binary representation.
That you need to add to any value.
Why do we
just with 4 bits available, there are 2 to the power of 4 minus 1.
With 2, yeah, 4 bits are available, so we have 2 over 4 minus 1. Another -1 because we favor the positive numbers.
-1, that's 7 negative values.
And these are 7 negative values.
So 7 is the number that you need to add to any value that you want to encode before converting it into unsigned binary. The value that you need to add is called the offset, or the bias. With an 8-bit exponent, which is the case for a 32-bit single precision real number in IEEE 754 format, the bias is 2 to the power of 8 minus 1 minus 1, which is 127. For a double precision real number, which has an 11-bit exponent, the bias is 2 to the power of 11 minus 1 minus 1.
So if we have 8, so it depends on the number of bits. It depends on the number of bits. because for 32-bit single precisions, we are using 8 bits to define them. We are raising this to 2 over 8 minus 1. Minus 1, it's 127. Okay.
Which is 1023. There's even a 128-bit quad precision format. The same formula applies. The big advantage of a biased exponent is the way that the values of different exponents can be compared easily. This is by virtue of the fact that the binary encodings are in lexical order, as are the denary values that they represent. Here are my 15 4-bit combinations, and I'm going to jumble them up. Now, watch what happens when I sort them as if they were text. This means the computer can easily tell if one number is bigger than another by comparing them bit by bit. This is not possible if 2's complement is used. Here are 2 examples that you might like to try yourself. Pause the video to give them a go, and I'll show you if what happens when I 4-bit codings, the values of different exponents can be compared easily. This is by virtue of the fact that the binary encodings are in lexical order, as are the denary values that they represent. Here are
so it's because they are in lexical order.
my 15 4-bit combinations, and I'm going to jumble them up. Now, watch what happens when I sort them as if they were text. This means the computer can easily tell if one number is bigger than another by comparing them bit by bit. This is not possible if 2's complement is used. Here are 2 examples that you might like to try yourself. Pause the video to give them a go, and I'll show you the solutions in a moment. The second example highlights a couple of important issues.
Convert 0. Wait. Okay. Let's do this. I like examples. Oops. Oops. So, let me do this. I have the sign. So the sign will be 0, right? Then I have 8 bits for, okay, let me remove this. I'm just gonna write it like this. So I have the sign, which is 0. Then I need to create the exponent and the fraction. How does the formula go? Where the fuck are you? You are somewhere at the beginning of this. Yeah, here. No? Exponent and mantissa. Yeah, exponent has 8 bits. Zero is positive. Convert to pure binary. What even is the number I need to convert? Wait. No, I don't want to see the solution. 0.09375. 0.09375 to binary. All right. So it's 0. Then I need to convert to pure binary. At first, I need to convert the number left of the floating point, but I only have 0, so it's gonna be, I assume it's gonna be, the exponent will be 1, 2, 3, 4, 5, 6, 7. This is the exponent.
To the decimal point of this result, 2 is not 1.5, when to stop sequence of bits, as you'll see later. Now, you need to normalize the pure binary representation.
Wait, no. I did something wrong here. It's not 8 bits in the exponent. It's 0. So it's only 1 0 point. So this won't be correct. It's gonna be 0. 0. converting the numbers right of the decimal point. So it's gonna be 0.9375 times 2, right? All right, let me, do I have a calculator somewhere? I have it here. Where's my calculator? So how many of these do I need to do? 0.9375 times 2. Times 2, it's 0.1875. 1875, still 0, so this multiplied by 2 is times 2 is 0.375, then I multiplied by 2, 0.375 times 2 is 0.75 times 2, 0.75 times 2 is 1.5. I remove the 1, it's gonna be 0.5 times 2 is gonna be 1. And that's it. So the second part is 0.00011, 0.00011.
When to stop, when the fractional part is 0. This method of converting from denary to binary is particularly good for spotting a recurring sequence of bits, as you'll see later. Now, you need to normalize the pure binary representation.
Then I do need to know.
The binary point is moved so that only one non-zero bit remains to the left of it. In this case, the point is repositioned 4 places to the left. To get the point back to where it was, you would have to float it 4 places to the right. So now you have the value of the exponent, namely 4. The normalized binary value is therefore 1.00
Wait.
pure binary. This is
So yeah, the sign bit is 0.
How we got there?
Pure binary, yeah, I'm here. So what is my next step? I know this, brother.
We've repeatedly multiplied by 2.
I saw
Remember
this.
to read the fractional bits from top to bottom. Step 3 is to normalize so we can get the mantissa and the unbiased exponent. Our binary value becomes 1.1 times 2 to the minus 4. That's how many places to the left we'd have to move the binary point to get the original value.
Wait.
Now we determine the biased
Now
exponent.
this is where
Remember to read the fractional
this
bits
is
from
where
top to
I
bottom. Step 3
tweak.
is to normalize so we can get the mantissa and the unbiased exponent. Our binary value becomes 1.1 times 2 to the minus 4. That's how many places to the left we'd have to move the binary point to get the original value.
How many places to the left we need to move the binary point?
Now we determine the bias.
Okay, so this is 1.1 times
exponent. In this case, minus 4 plus 127. That's 123 in base 10, and when converted into 8-bit binary, we have the bit pattern you can see here. In step 5, remove the leading one from the mantissa, so we simply have 1. And finally, you can assemble the result. We padded out the mantissa with zeros to make it up to 23 bits.
Alright, so I understand the process now. The mathematical process of this is fairly simple. I don't understand how it happens. I don't have no clue on why it happens like this. I can understand the mathematical background of it. I can follow the steps basically, but why the fuck would we do all of these things? That's something that's a mystery to me.
In the second example, the sign bit is a 1 because it's a negative number. When we convert this into pure binary, this is what we get. Now I'll show you how we got there, but first of all, let me point out that the last 4 bits are recurring. That's why they've been overscored and there are 3 dots at the end. To get the whole number part, we divide by 2.
Yeah, the same thing. So
it's pretty straightforward. Remember to read the bit pattern upwards for the whole number.
Sorry. So it's the same thing. We divide by 2, we get the remainders. We just basically convert the number without the decimal point into a binary number. Okay.
To get the fractional part, you repeatedly multiply by 2. Now, as you're doing this, you'll notice that the value 0.6 comes up again, in which case you have a recurring bit pattern.
Oh, so it's
There's
a
no need to
recurring
keep
bit
going.
pattern.
And remember to read this sequence of bits from top to bottom. Now we normalise to get the mantissa and the unbiased exponent. The point has to move 6 places to the left in order to follow the leftmost one. An exponent of 6
wait. 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. Okay, so this is
the point has to move 6 places to the left in order to follow the leftmost one.
yeah, here we move it to the left.
An exponent of 6 now needs to be converted into a biased exponent, so we add 120.
And here we moved here we moved it to the left.
27, which is 133, and that is converted into an 8-bit unsigned binary integer. The leading 1 is then removed from the mantissa, and we make the mantissa up to 23 bits. Now, there's an extra step that you could perform at this point. The mantissa includes a recurring bit sequence, which means it's too long to be stored with a finite number of bits. You might choose not to do anything in particular about it and simply chop the mantissa at 23 bits to make it fit. If you check your result with an online calculator, you might see that the mantissa has simply been chopped. Simply chopping the mantissa is effectively rounding it down. But in reality, a computer will round the mantissa either up or down to the nearest value. Some online calculators will round the result properly. If you want to round your mantissa properly, ask yourself what the 24th bit would have been if there was room to store it. If it would have been a 0, you can simply chop. If it would have been a 1, which is the case here, then you should add 1 to the mantissa. This is a regular binary addition operation, so it might generate carry bits that need to be dealt with. When it comes to rounding, there is a special case in which the 24th bit is a 1, followed by nothing but zeros. In this case, if the 23rd bit that you are able to store is a 1, then you add 1 to the mantissa. If the 23rd bit is 0, then you chop. I'll talk more about rounding and rounding errors in another video. The final job is to assemble the result.
Okay, so
here are 2 conversions in the other direction that you can try if you wish. Solutions to these in a moment.
So how is this done? I chop off the first bit, that's gonna be the side, then I chop off 8 bits.
And here are the solutions.
Oh, how?
For the first example, determine the sign.
Okay, this simple.
The sign is positive because
it's
it starts with a 0.
positive.
Then determine the exponent in denary. The exponent bits represent.
Okay, so these are the exponent bits. We only take 8 of them. In binary, these are 132. How can I now
set the value 132?
Okay.
Now we need to remove the exponent bias.
The exponent bias is 127.
So that means subtracting 127.
All right.
We have an exponent of 5.
It's 5.
Convert the mantissa to denary. The significant bits of the mantissa have been put into this place value gadget. This gives us the value 0.828125. Now we add 1 to the mantissa and we include the sign. And then we can calculate the final result. We have 1.828125 times 2 to the power of 5. If you do this on the calculator, you'll get 58.5. Calculate 2 to the power of 5 first, and then multiply this by the other value.
All right.
In the second example, the sign of the number is negative, because the sign bit is a 1. Now, determine the exponent in base 10. In this case, it's 9. We need to remove the exponent bias, which means subtracting 127, so we have an exponent of minus 118. Then convert the mantissa into denary. Plugging the binary digits into the place values gives us 0.09765625. Add 1 to the mantissa and include the sign, and we can calculate the final result. We want the result in base 10, so we have to multiply minus 1.09765625 by 2 to the power of minus 118. This will give you a purely base 10 result, which you can see is rather small. You can leave the result like this if you wish, or you can float the point to the left, but you'll have to think about doing some base 10 rounding at the other end.
Okay.
To finish off, I'll briefly mention a couple of exponent values that have special meanings, depending on the value of the mantissa. If the exponent bits are all 1s, and the mantissa is all 0s, the number being represented is infinity. If the exponent bits are all 1s, but the mantissa is not all 0s, then the value being represented is not a number. If the exponent bits are all 0s, and the mantissa is all 0s, then the value being represented is indeed 0. If the exponent bits are all 0s, and the mantissa is not all 0s, the value being represented is very, very small. This is known as a subnormal or denormalized number. These are the topic of another video.
So this was incredibly explained. I understood the mathematical background of this. I understood how it's converted. I'm still unsure of why we do certain steps. But mathematically, I could now convert a floating point number to a decimal one without issues, without trouble. But why? So I'm still unsure why we use 127. I'm still unsure why we move the decimal points left or right. The thing about repeating numbers, it seems like a more complex topic, so I ignored it completely. So there are a couple of things that I'm unsure of. Interesting. So let me stop here. It's 5 minutes to 12 where I'm from, and I should get a good night's sleep tonight. So let me stop right here, and I'm gonna continue. So this was the first part. I expected to understand the fast inverse square root algorithm in this video, but it seems that the topic of it has a lot of underlying components that are, for me at least, unknown. So I'm gonna stop here. Today I started with the fast inverse square root algorithm, but in the end I could only, hey Jacob, I'm only hi. So what I did now, I'm gonna do just a recap. I started with this. I wanted to understand this because this is something that I came across like multiple times. But somewhere down the line, we started talking about representation of 32-bit floats, and I'm quite rusty on them. And this doesn't. It's something that I lost knowledge of. So I just wanted to remind myself on how we do this. And I think now I have a better understanding of it, so I can, in the next episode, in which I will most probably continue where I stopped here, I think I will do a better work of grasping this. So thank you all for watching, and see you some other time. Thank you and see you. Bye bye.